Hello guys, in this lecture I would like to explain about random walk process. I will discuss about the concept, the theoretical concept of the random walk process, and I will give some examples from the real life, and then I will explain that in how we can generate a random walk process in R in RStudio. Uh, for this lecture, you need to know about the stochastic process and then the random process, the purely random process. I completed these two lectures before this, so I will mention the link of the purely random process. I mean that the link is mentioned in the description about the purely random process. So you can see the purely random process uh, by clicking on the link in the description of this lecture. Let's move toward the theoretical background. Purely random walk process. A random walk process. Suppose ZT is a discrete time purely random process with a mean mu and variance sigma square z. I already told you that you need to know about purely random process. So you can see this video and the link mentioned in the description of this lecture. Okay, suppose this is a variable, a purely random process with mean mu and variance sigma square z. A process xt is said to be a random walk if this can be expressed like this. This means that xt depends on the previous value plus some error term or some random variation, you can say, some uncertainty. The process customarily started at 0 when t equal to 0, so that x1 equal to z1. Of course, I would like to explain this by doing on the board. Okay, you can see in the random process you can write by the random walk process you can write by xt equal to xt minus 1 plus zt. Okay, let's choose. Okay, okay. I think this is fine. Okay, okay. So z. Okay, and this is zt is the random error, and you can see that xt that means that the process current at the current time depend on the previous time plus some variation, and you can see the assumption of zt is a process discrete time process purely random process with mean mu and variance sigma square. So this is the process. So now they says that if the process start at t equal to 0, at t equal to 0, this means that uh, the process has the process customarily start at 0 when t equal to 0. So the value of t, this means 0 is equal to t0, so that x1 equal to zt. This means that let's suppose t equal to 1, t should be 1, because if t is equal to 0 then xt minus 1 does not make any sense. So x1 is equal to x1 minus 1 because t equal to 1 plus z1. So this means that x1 equal to x naught plus z1. And remember that at the initial, I mean the starting point, the value is 0. So this means that x1 equal to z1. This can be explained in this way, that y is x1 equal to z1. And then they says that xt equal to I from 1 to 2 zi. So this is equal to 1, then you can put the values of xt minus 1 and then x2 minus 2 and so on. So you will get this expression. Let's see how we can do this. Let's start again from xt, that is equal to xt minus 1 plus zt. And remember that if xt equal to xt minus 1 plus zt, then xt minus 1 is equal to xt minus 2 plus zt minus 1. Just put this value in this equation, you will get, just put this, this is equal to xt minus 2 plus zt minus 1 plus zt. Again, put xt minus 2, uh, then xt minus 2 equal to xt minus 3 plus zt minus 2. And you can put this here. This will be equal to xt minus 3 plus zt minus 2 plus zt minus 1 plus zt, and so on. You can put now the value of xt minus 3 and so on. So at the end you will get, uh, the, this is I from 1 to t. So at the end you will get, when x is equal to t, then this will equal to x t minus t plus zt minus t minus 1. This should not be t. Oh, okay. Yes, this should look like this. Yes, it should look like this. Plus zt minus 1 plus zt. So this is equal to then xt equal to x naught plus z1 plus z2 plus up to zt minus 1 plus zt. You already know that the process start at 0 point, has a value 0, x naught equal to 0. So this means that xt equal to z1 plus z2 plus zt minus 1 plus zt. So this is equal to xt equal to, you can write like this in the compact form, that I equal to 1 up to t, whatever mentioned in the slides. It's depend on you. You can write by yourself whatever, but it is mentioned up to t. So you can write up to t zi. So this you can write like this. This you can express the Beverly random walk process, the random walk process like this. Now this have some properties. You can see that. Uh, then we find that ext is equal to t mu. You can prove this in one or two steps. Just look how you can do. So this means that xt equal to, you already know that this is equal to this one. You reduce this to from 1 to t and zi. So now e of xt equal to m expected value of this expression I from 1 to t zi, and this is equal to, now you can write this, or you can expand and apply e on each zi, and then you can sum, or you can write like this, whatever you want, zi. And you already know that this is the assumption that zi has a mean mu and variance sigma square I. You can see it is here. Random process with mean mu and variance sigma square zi. So each zi has a mean mu. So this means that I from 1 to t, and this is now equal to mu. because we already know this. So you are summing this mu t times, so this means that this is equal to t mu e of xt equal to t mu, which is one of the property of this process. You can see with t mu and variance t sigma square. You can also calculate the variance. Now the variance of xt is equal to variance of I from 1 to t zi, which is equal to I from 1 to t variance of zi, and which you already know that I from 1 to t. You know this variance is sigma square zi. This is mentioned in the assumption sigma square z. So this is now a constant and you are summing this t times. So this is equal to t sigma square z. This is just like you can say, suppose you are summing sigma square z plus sigma square z and you are summing this n times suppose. So this means that just take this constant sigma square z and you are summing 1 n time. So definitely this is equal to n and the whole quantity as sigma square z. So this is the variance of xt of the random walk process. Okay, now let's see what are the other properties. Okay, z are independent as the mean and variance change with t. The process is non-stationary. Okay, this changing in the mean and variance is due to time with the time, so it's not a stationary process. However, when you are taking the first difference, this means that when you are taking the first difference, mean that when you're subtracting xt from both sides, you can get the process zt, which is random walk, or you can say purely random process. So that is stationary. You can see like this. You can make that equation in this way. Again, I will start from the random walk process that is equal to xt minus 1 plus zt. When you are taking the first difference, you are subtracting xt minus xt minus 1. Subtract xt minus 1 from both sides minus xt minus 1 plus zt. Cancel, and this is now the first difference. You can write like this is equal to zt, which is of course normally distributed and variance with mean mu and variance sigma square z. So this is purely random process and this is of course the first difference as stationary. You can write this like xt by definition xt minus xt minus 1. So this is just the definition of this difference operator. Okay, so this is now a stationary. The first difference is stationary. The features can be used to construct a random walk. This feature can be used to construct a random walk. For instance, figure 3.2 shows a random walk series and its correlateron. The best known example of time series which behave like random walks are share prices on consecutive days in the stock market. A model which often gives a good approximation to such data is as share price on day 2 is equal to share price on day t minus 1 plus error run. This is just the the random walk process there. This means the share price is at day t, that is xt equal to share price at day t minus 1, that is xt minus 1 plus zt, that is error run. So this is all about theoretical concept of purely random walk process, of random walk process, sorry. Now I will show you that how we can do this and or you can see this is the figure 3.2 which is mentioned on this slide here, that they generated this series by using RStudio using this code, and then they draw the original data and the correlation, the autocorrelation function. So let's see how we can do this in RStudio. Okay, again, I will see. Suppose we are drawing 500 observations. I will put n is equal to this one, and then okay, we're drawing. We simulate 500 observation from our normal distribution, that is n is equal to 500, which is mentioned above, with zero mean and unit variance. Okay. Uh, okay. So this means that this is a purely random process in this case, as mentioned in the theoretical part, in the theory of the random walk process. And then we will make, from this we will make purely random walk process from purely random walk process. So let's run this. Okay, this is working. This is working. And now I need to use a function CumSum. This is a random walk. Random walk is assigned to this function, and this will sum this function. This the random the purely random process by using this function. I need to little talk about this function, that how this work. You can just write question mark. Um, okay, this is another dimension. So you just need to click to write the question mark and then the function, and then click on the enter, and you will see, okay, this is cumulative sum, product and extreme. So we are just using this command, cumulative sum. We are cumulating summing this. Remember, we are cumulating summing this. And you can see in the theoretical part that why we use this function, because you can see that this is cumulative sum. If you see this, my derivation, you can see that this is cumulative sum, because you can see that xt is equal to this one, but then x1 is equal to sum of these two variables. And okay, so you can see in the end, this is the cumulative sum of the random process. I mean that xt equal to 2, suppose. Here you can see xt equal to 2, t equal to 2, so this will be equal to z1 plus z2, x3, this will be equal to I from 1 to 3, z1 plus z2 plus z3, and if suppose x equal to t equal to 5, this will be the sum of until from 1 to 5, z1 plus z2 plus z3 plus z4 plus z5, and so on. Therefore, you don't need to look at here, because this is the result which you derived from here. So this is the same thing, but maybe this is not. This is a bit difficult for you in RStudio. So you can do the function CumSum and just get the random walk process. The random walk process, yes, in RStudio. So this function is look like this, and this you can use. We already used this. Now you generated the random walk process, and you can plot the original series as well as their ACF. Again, I explained this in previous lecture, but you can see in the description again, and you can see what is mean by this function. Okay, this is just divide the screen with different margin for each side, and now I need to plot the ACF and the PACF on this data. Okay, so this again, this will just plot the original series, which is random walk calculated by this function CumSum. And let's do this. Yes, you can see this. This is the series. The original data, the graph is little, the space is less. And this is now you can draw the autocorrelation function. So these are these two. Uh, if you don't use this command, just try this, because I don't need. Uh, you can see please that time is mentioned here, series is mentioned here, n leg is mentioned here, and this autocorrelation function, and this is the original series. I'm just removing this because to make little bigger graphs, removing this margin because the margin is too much and the graph is not looking okay because this is space is given to the graphs. You will see now better graphs, but in the paper or in the publication you don't need because you need an x-axis and y-axis the labels. So you need to use some margin or you don't need to use margin. You can use by default. You can see like this. Okay, this is little, you know, more, but um, uh, you can plot these independently. Like I mean that you can plot these both the original uh, series and the autocorrelation function separately. Suppose I'm using this. Okay, I'm using this. I don't want to divide my screen into different parts. So you can see this is now the series. This is the series and you can see the series which is developed. It's look like this, but I think it's not necessary because you are randomly generating the data. So it's not necessary, it should be the same. It's not necessary. Okay, let me do like this and just dividing this into two. If you want to see the two graphs, then you need to margin, make smaller the margin and do like this. I think it's better now. Okay, it's look like this. Okay, let me again generate the values and then see. Look, the graph is now different because this is the cumulative sum of the purely random process. So it can be not, it's not necessarily be the same. So it is now changed. You can change the legs because this is until 25 legs. You can change. You can increase the legs by just adding this command. This option leg is equal to, suppose this is until 25. You can make this until 50, and again plot these two data set. The original is this one, and the other is this one. So you can see this is a decline, slowly decline of this process. So this is the original series, and this is the autocorrelation function, and you can see here the same thing. This is also decreasing, and this is this is of course a random walk process. So this was all about random walk process, the theoretical concept and some statistical properties, and then how we can work with the random walk process and or how we can generate a random walk process and R. I hope this helped you, and I mentioned already the description, in the description the link to the previous video that is about purely random process. You can see and you can understand the concept because that is important for this lecture. If you like the content, please subscribe the channel and see you with the next video. Ciao.